Hello, everyone. Good afternoon, and welcome to this edition of Live from NOIRLab at Arizona. I'm your host, Rob Sparks, and our moderator, Jamaica Marshall. Tomorrow we'll be celebrating Citizen Science Month, April Citizen Science Month, and we have three guests who will be telling us about various citizen science programs at NOIRLab. We'll hear about Globe at Night from Connie Walker, Backyard Worlds from Aaron Meisner, and the local group cluster search from Knut Olsen. Remember, if you have any questions or comments, please type them in our chat and Jamaica will relay them to our guests. First, I would like to tell you a little bit about Kitt Peak National Observatory. Kitt Peak is funded by the National Science Foundation and is a NOIRLab facility. It was founded in 1958 and is located about 55 miles southwest of Tucson on land leased from the Tohono Nation. We are indebted to them for letting us use one of their sacred mountains for astronomical research. Kitt Peak is home to over 24 optical telescopes and 2 radio telescopes. And we just have a quick news update from Arizona here. Just recently, Arjun Day, an astronomer at NSF's NOIRLab in Tucson, has been awarded a John Simon Guggenheim Fellowship in Astronomy and Astrophysics for 2021. Guggenheim Fellows are appointed on the basis of past achievement and exceptional promise for future accomplishments. Since 1925, the Guggenheim Memorial Foundation has awarded annual fellowships in the arts and sciences. This year, the foundation awarded 184 fellowships from nearly 3,000 applicants, but only 2 in astronomy and astrophysics. From the Guggenheim announcement, in all 49 scholarly disciplines and artistic fields, 73 different academic institutions, 28 states, 2 Canadian provinces are represented in this year's class of fellows, who range in age from 31 to 85. Day will use the grant to spend time exploring NOIRLab's existing survey data in search of fast-moving faint stars, using these to investigate the structure of the Milky Way. We congratulate him on this award. And I'll mention that this is the second year in a row we've had a Guggenheim Fellowship awarded to a NOIRLab astronomer. Last year, Joan Najita had an award for her. So congratulations to Arjun Day on his award. So now let's move on to the first of our guests. Let's see here, I have the bio down here. Yes, Knut Olsen is a staff astronomer and the Community Science Data Center principal data scientist at NSF's NOIRLab. He started work on the Magellanic Clouds through his PhD thesis with Dr. Paul Hodge at the University of Washington and continues exploration of them while living and working in La Serena, Chile. He now lives and works in Tucson, Arizona. So with that, I'd like to welcome Knut Olsen to us so he can talk about his citizen science project, which I believe is complete now, is it not?
Yes, although we're still looking at the results of it, and there's actually more to do in the future once the data is ready to go.
Okay, super. Well, I'll let you take it away.
Okay, great. Let me start sharing here. Okay, can you see the screen okay?
Yes, you're good.
Okay, great. Okay. Yeah, so thanks for having me on to participate in this tag team presentation on citizen science. I'm going to talk a little bit about how citizen scientists helped advance some research on star clusters, and hopefully that will be a good story to tell. So first, what is a star cluster? So you're probably already familiar if you spent any time looking up at the night sky with a few examples of star clusters. So up here on the top left, whoops, is the Pleiades star cluster, is also known as the Seven Sisters. It looks, it's a piece of a constellation in the night sky, but it's actually also a star cluster. And this, to the right of that is the Hyades star cluster. So this is also, it's part of the constellation Taurus, actually forms the horns of the bull in that constellation, but is also a star cluster that is of interest to scientists. And around the rest of the slide here are various images of star clusters of different types, different shapes, different sizes, and turns out different ages and chemical abundances that that all provoke sort of, questions driven by curiosity about how star clusters form, what role they have to play in galaxies, in star formation. You can ask questions like, well, do stars and star clusters, are they different in any way from other stars? Do they have planets, for instance? These are all really interesting questions that that require us to build up samples of star clusters. So a couple of questions that have excited astronomers for a while is we know that star clusters form. So here on the left is a picture of the antennae galaxies that are colliding, and colliding galaxies, when you're smashing together the gas and dust from which stars form, turns out to be a very good way to form lots of star clusters. So in these galaxies, a lot of the points that you see in those images are actually individual star clusters, and the youngest, most massive star clusters are causing the gas around them to glow red because it's ionized. So lots of star clusters there. We also know that star clusters don't survive forever; they can dissolve. So here is an image of a part of the sky containing the star cluster Palomar 5 that by picking out the stars that belong to the cluster, you can see these spectacular tidal tails that indicate that the star cluster is actually losing stars along its orbit and dissolving. So, questions of how star clusters form and how they evolve are tied into many different astronomical questions. And why star clusters are so useful as both in their own right and as tracers of what might be going on in galaxies and with star formation is indicated in this simulation. So here I've taken a simulated image, and I actually used this in my previous NOIRLab live talk too, so some of you may have seen it before. But this is showing what a star cluster might look like when it's very young, when it first forms. And the thing about a star cluster is, imagine that the stars all formed at mostly the same time under the same conditions. And if you take these stars and you measure their luminosities and their temperatures and you put that on the diagram, then that measurement lets you pinpoint its age and chemical abundance. So since this is a simulation, I'm going to advance the age of the cluster just by hitting play here. You can see that very quickly the cluster loses its blue stars because they all blow up. And what's left is the lower mass stars, which evolve more slowly, but when they evolve, they turn into red giants and turn red. And so by looking at this sequence, you can pinpoint the age and the metallicity, the chemical abundance of stars in the star cluster. And that's really useful information for trying to trace the history of galaxies, understanding star formation, etc. So a lot of these questions around star clusters, you need, if you want to understand sort of how a galaxy is put together from its star clusters, or what a star cluster says about a galaxy, you need to find them. And that could be a real challenge. So here's a picture of the Andromeda Galaxy, or a piece of it, taken with the Hubble Space Telescope as part of the FAT survey. That in this image are literally thousands of star clusters. Some of them you can already pick out by eye here, but in order to find all the star clusters and be able to answer questions about the population of star clusters, you need to do this systematically. And that's hard to do. In fact, our team of scientists who first started doing this took several months to try to find all the star clusters, and also worked very hard to try to define basically software, computer software that would find them automatically. But it turned out that people are much better still at finding these objects than machines are. And so this is a 1/4 degree of sky about. Here is another galaxy that I'll talk about, the small Magellanic Cloud. This comes from the dark energy camera on the CTIO telescope at NOIRLab as part of the SMASH survey led by David Nidever. This image is a couple of degrees across. There's also hundreds of star clusters here, a couple of really obvious ones. This big red one up in the upper right-hand corner is 47 Tuc. It's a galactic star cluster, in fact. But most of the other clusters are in the galaxy here. And so finding this requires poring over a huge number of images, which is, if it had just been a bunch of astronomers looking at them, would have taken years rather than months. Here is the large Magellanic Cloud. So this image is about sort of 8 degrees on the side, so much larger area. Finding the star clusters in this galaxy is an even bigger challenge just because of the amount of imaging that has to be gone through. So we've tried with small groups of astronomers, we've tried with developing automated software to find star clusters. What turns out to be one of the best ways to find them is to involve citizen scientists. So here, this really started with the Andromeda project that Cliff Johnson led this project using that Hubble imaging that I was showing you of the Andromeda Galaxy, and enlisted the aid of hundreds of citizen scientists in identifying star clusters in these images and reporting what they saw. I'll just show that again. So it really was just looking over images, identifying interesting looking objects, and labeling them. And the thing that makes people really good at this is they can tell that something like this is possibly an interesting star cluster, whereas just this is a small group of stars that could easily fool a machine into thinking it was a star cluster. With the group of citizen scientists that we had, basically within a few weeks, they were able to look over all of the data and find the star clusters in them. And moreover, we could actually, so Cliff injected artificial star clusters into the images that the citizen scientists would also find. And in that way, we could measure not just the star clusters, but how well people were at identifying them. So we found thousands of star clusters through the help of the citizen scientists, as well as lots of background galaxies, which were interesting. You can hear Cliff describe this project at this YouTube link. But just to show a couple of the results here. So here are the star clusters that were found in Andromeda all over the sky. You can see that they kind of cluster along these spiral arms. And here are the background galaxies. So these are galaxies in the background of Andromeda that are shining through. And they help tell where the dust is, right? So here you don't see so many because there's all this dust in the way in the Andromeda Galaxy, whereas you do find star clusters there. Anyway, I'm gonna move very quickly on to the clustersearch.org, which was started with finding star clusters in the small Magellanic Cloud, that second galaxy I showed you. That search has been finished. Basically, the team of citizen scientists over the course of a couple of months classified 580,000 objects and more than 8,000 images, and found hundreds of star clusters. And here's just a small gallery of the kinds of objects that they found. And we can now use these to answer questions that we're interested in about star cluster formation, about comparing them now to the Andromeda Galaxy, comparing what makes these populations of star clusters different in the small Magellanic Cloud compared to Andromeda, for instance. So the next search that is going to start up soon is that in the Large Magellanic Cloud. So keep an eye out for that. But the kinds of things that we are able to do with star clusters are now compare the galaxies like M31, the Andromeda Galaxy, and the LMC. You can see that they're star clusters, for instance, trace the star formation that's in those galaxies. And so now we're be able to get at the sort of the physical origins behind star cluster formation. And so there's more to come. It's a work in progress. This is my last, yes? Oh. Yep.
If you have just one more slide, then maybe I can wait, but we do have a couple of questions for you in the chat.
Sure. Yeah, this is just the very last slide I was going to leave. So, star clusters are really intriguing objects and beautiful in their own right. And I just wanted to leave with sort of a picture of one of my favorite star clusters, which is a globular cluster in the LMC, the Large Magellanic Cloud, that also caught the eye of Phil Plait, the bad astronomer, who wrote a blog post about this. So check that out if you're interested. But okay.
Yes, Phil Plait, the bad astronomer. So, well, we have a couple of questions. So let me take them out of order because I think this question probably should come first. And this is from what's his name is? I believe it's Chimmy. And the question is, what is the difference between a star cluster and a galaxy?
Yeah, so that's a good question. So it's so galaxies are very large objects, right? So the Milky Way galaxy is a galaxy, the Large Magellanic Cloud is a galaxy, etc. So in one and star clusters are much smaller. So that's one difference. Basically, star clusters are collections of a few thousand to a few million stars. Galaxies tend to be billions of stars. So there's a question of size. But there's probably also quite different physical origins. So we think that galaxies formed basically by accreting material onto seeds of dark matter, right? So we think that the universe is filled with these concentrations of dark matter, which we call dark matter halos. And those were the seeds on which galaxies grew. Whereas star clusters are a mode of star formation that happens that doesn't involve dark matter itself. So it's just when you concentrate lots of star forming material into one place and you apply enough pressure for them to contain the star formation that happens, we think we form star clusters. So dark matter seems to be the key difference. Also, of course, the difference in scale. But it's a great question because if you go down to the very faintest galaxies, you start to find galaxies that have about as many stars as a star cluster does, and so that question starts to become difficult to answer. And that's where we think the role of dark matter is really important. It's just a different way of forming concentrations of stars. Great question.
That was a great answer. Thank you. Okay, and so then you were talking about the first citizen science project that you brought up in your presentation, and Alan Jackson, who joins us often, and we're so glad to have returning viewers. Alan wanted to know, was that a Zooniverse project?
Yes, it was. Yeah. In fact, the Andromeda project was on the Zooniverse platform, and also clustersearch.org used the Zooniverse tools, the platform to do that. So the Zooniverse is a really nice interface right? You can easily discover lots of different scientific projects that you're interested in, and yeah, it really helps make it go. Yeah, I should have mentioned that. Thank you, Ellen.
We appreciate the question, Alan. And one last question just for me before we go to our second presenter. There are differences in star clusters, the types. In general, there's maybe two large ones, open clusters and globular clusters. And I believe you definitely talked about globular clusters. Could you give us a quick definition, difference between those two? And then I think we're transitioning to our second presenter after that.
Yeah. So again, it's you can look at sort of the extremes. So globular clusters, the classical ones are very old, highly concentrated, and fairly massive. And open clusters, we on the whole, think of as more diffuse, less concentrated, usually less massive, and somewhat younger than globular clusters. But there are crossover objects. There are objects, massive young star clusters that we see forming, sort of in the present, that we think will evolve to something like the globular clusters. Which were among the first objects to form in the universe. And there are open clusters that are quite massive and approach in appearance and in some properties like those of globular clusters. So the lines are blurry, but those are, I would say, the main differences.
Thank you so much. We appreciate that. And if we get any other questions for you, we'll be sure to send them on to Rob so that we can answer them. Yeah. Thank you so much.
Thanks very much.
Yes, Knut has to go now because of our family obligation, but there's a great comment in the chat too. I don't know if Jamika saw it because it just came in. Chemi says that also makes me think about how massive objects like black holes can play a crucial role to create galaxies from star clusters. And I believe that the role of black holes in galaxy formation is a pretty active area of research, isn't it?
Yeah, and in fact, there's black holes at the centers of very massive and dense star clusters is an interesting question. We think that some of these massive globular clusters probably harbor black holes at their centers.
Cool. Thank you, Knut. Next, we'll bring on Connie Walker. Connie is an astronomer who works mostly on dark skies advocacy and education. Inspired by an early age from astronauts landing on the moon and the original Star Trek series, her curiosity for anything astronomy propelled her to be the first in her family to go to college and get a PhD. Connie's been a scientist at NOIRLab for 20 years, creating, with the education team, innovative programs on dark skies education as well as optics and astronomy programs through inquiry and research to excite teachers and students in STEM, and then sharing these programs via workshops, talks, and events all over the globe. She holds some leadership positions with the International Dark Sky Association and the International Astronomical Union, where she is heavily involved with light pollution issues on the ground, and more recently in space with satellite constellations. Of cool things that discoverers Levy and Shoemaker named asteroid 29292 Connie Walker for her efforts in education outreach. And Connie also pointed out that today is also Earth Day, which I thought I'd mentioned here since Earth Day is connected to her citizen science project. So let Connie take it away at this point.
Well, thank you, Rob. Thank you, Jamika. It's a pleasure to be on this program. A pleasure to be here to meet everybody virtually. My name again is Connie Walker, scientist at NOIRLab, and that's your national observatory, basically. And I have been asked to talk about measuring the light at night with the citizen science program known as Globe at Night. I would hazard a guess that people in general are not willing to drink polluted water or breathe polluted air or have their yard polluted with litter. Many are willing to do something to protect those landscapes because basically it affects their lives. The pollution affects their lives. But what about something like light pollution? So I have here a picture for you. I want you to imagine that the landscape in this instance is the night sky. And it's the most beautiful starry night sky you have ever seen. So many stars that you cannot tell one constellation from another. And the Milky Way is arching overhead so bright that it actually casts a shadow of you on the ground. And believe it or not, this happens. These kinds of scenes actually exist, but they're slowly disappearing. Would you be willing to protect the starry night sky from light pollution? And let me tell you, of all the pollutions, it's the easiest one to protect against. And let me tell you why. So I just want to first have you imagine again that you're in one of these cities you see here. And what kind of sky would you see within those cities looking up? And of course, the stars will be washed out. You'll be, enveloped by light pollution, basically. The rate of light pollution is about twice the rate these days of the growth of the Earth's population. And that's kind of sad. And even with 80% of people in the United States never being able to see the Milky Way arch overhead, people are still taking notice these days more and more, which is good, and that the night is a treasure to be protected. So what are things we do lose when we no longer can see a pristinely night sky? Well, inspiration is pretty much at the top of my list, and cultural heritage being lost is at the top of my list. But practically speaking, there's basically billions of dollars each year that are wasted in energy consumption through unshielded lights, where the lights are shining up into the sky and they're not shining where they're needed, and they stay on longer than they're needed. So that's one thing. And glare, which is also shown in this picture in the upper left, is a big problem, especially with aging eyes. That it creates hazardous situations, and like trespassing into your bedroom window too also kind of disrupts your sleep. And then there's circadian rhythms, or circadian sensitivities, they call them, that can be disrupted, and they're kind of connected to things like obesity, depression, sleep disorders, and even diabetes, believe it or not. So the melatonin in your body actually gets depleted during the day, and it has to be repleted, or restored at night. And if you don't do this, if you have too much blue light basically at night, even indoors primarily, it doesn't replete, and that actually is being studied and shows to have ties to a couple different kinds of cancers. So there's all these different things that are very relevant to your lives, but also to the lives of animals. So the habits and habitats of animals are very negatively affected in some cases. So you have some that are pushed to the brink of survival. So you have birds that are migrating that are confused by city lights. You have sea turtles that are just hatching and are confused and they don't make it back into the ocean. There's all sorts of things that happen. And I don't mean to frighten everybody, but these are things that do happen. And of course, a washed out sky impedes astronomers too from viewing and researching to understand our universe and our origins, as Knut went over. So there's some very simple actions that can be taken on your doorstep, in your home, and around your home. And you can ask if your outdoor lights serve a clear and necessary purpose. Keep the ones that do and turn off the ones that don't. Is the amount of light appropriate for the intended task? It might be too bright, so you can reduce that. Are the light bulbs energy efficient? Does light fall where it's needed? Is it properly shielded and directed so it hits the ground and not your eyes, basically? Is the light connected to active controls like timers and motion sensors? And does it have a warm color, like a yellowish red color, which is less harmful because it's not emitting the blue light, basically? So the International Dark Sky Association is the place to look for more information. And I have their their URL there at the bottom right, darksky.org, if you want more information. They are the experts. But the other thing you can do, and this is my long intro to Globe at Night, I guess, is to actually participate in a very simple citizen science program. Because, like Knut was mentioning, we cannot, as scientists, be everywhere around the world taking data. And it's very essential that we have people like feet on the ground to look up at the night sky and take our measurements for us. And so in this case, we're talking about light pollution. So Globe at Night is a very, I'm biased. It's a successful international citizen science campaign to raise public awareness of the impact of light pollution. And it's been running for about 15 years in 180 different countries. And about 2/3 people have participated. And just last year, we had nearly 30,000 measurements taken from over almost 100 countries or so. So this worldwide campaign involves the public in recording the night sky brightness by matching what they see, their view of a constellation for that particular month. Like in January and February, it was in March it was Orion. This month it's Leo. Next month it's going to be Boötes. And then to match what they see with these charts that we offer them at our website, on our web app, we call it, or report page. And this is done over a 10-day campaign every month. And that 10 days, that changes because the lunar phases change. So you don't want the moon up in the first half of the night because it's going to be like a natural light bulb in your night sky. So we avoid that. And so just to get you introduced to the webpage, this is what the first page looks like. And you can see at the very top, it has all these tabs for learning and observing and reporting the observations that you make and the maps that are resulting from it pretty much automatically, and the data that you can access for projects that you may want to do, and other resources as well. And the report page is what you want to access, though, when you are taking the globe at night measurements. Then to take those measurements for globe at night, you first want to go out over an hour after sunset, because then it's really dark and you can take good data when it's, really dark out, as dark as it can be in your location, that is. And you want to turn off as many lights as you can when you make your observations, things that you yourself can control in terms of lighting outside, and even light from the inside that if the windows are unshielded themselves, you might turn off those lights as well. And you have to get, the thing that's going to take the longest part of the time is getting your eyes adjusted to the dark. It takes about 15 minutes for your eyes to adjust to darkness. And then you'll take some good data after that point. It only takes about 1 minute or less to take the data. Okay, sorry. And so, so then you're going to find the constellation in the night sky that Globe at Night is using that month. And so maybe you have an app like Star Walk or something similar that can show you in the night sky where to find the constellation. Leo is kind of easy because it was a big, nice question mark, backwards question mark in the night sky that you could pretty well distinguish. And it's a little bit more challenging for Boötes, but those Star Walk or those other kinds of software planetaria on your phone are very easy to use, and a lot of them are free. So to take measurements, you can go to the Globe at Night website at globeatnight.org, or you can click the report tab, or you can use the link that's shown on your screen right now. And the web app is synonymous for us to the report page. So here's the first 2 steps on the report page that you'll see. The first step is to enter the date and time. And the second step is to either put your location where the observation was taken. And that could be your street address, if that's where you were, where you took your measurement, or it could be the intersection of 2 streets. We don't really keep the data. It translates into latitude and longitude. So don't worry about that. We don't keep that kind of data. Or you might have a landmark that you're standing next to, like if you're standing next to the Eiffel Tower or something. That'll be very light polluted sky, but anyway, I'm just giving you an example. And that's the kind of things you can do. Or if you know your latitude and longitude, you could put that in. That would be great. Any of those. So if you have a smartphone, the really cool thing is that these first 2 steps are ones you don't have to put any data into, because your smartphone will automatically put the data in for you, which is pretty darn cool. It's almost very little you have to do in this citizen science program, to be honest with you. So, so the star charts you'll be using, let's see if I might have missed a step here. Yeah, I did. There we go. Okay. The star charts you'll be using to determine the light pollution levels where you live are defined by actually the faintest star that you see. You're not counting stars. So you're going to have 7 charts to choose from, and each chart has progressively fainter and fainter stars on it. So there's more and more stars that you'll see on each of the subsequent charts. So chart 1 that you don't see here, but you'll see in a few minutes, is like what you would see in New York City. You might have, 12 stars across the whole sky, when you should be seeing thousands if you didn't have a light polluted sky. And chart 3 that you see here is typically what you see at the center of a medium-sized city like Tucson, Arizona, where I live. Chart 5 is like what you would see if you could just start seeing the fuzzy Milky Way overhead. And chart 7 is what you would see in a national park with so many stars you can't tell one constellation from another. So you're just looking for the faintest star and you're trying to match what you see with that particular chart. So this is the charts that you would use for this next month. The campaign starts on the 2nd of May and runs through May 11th. And it's towards Bootes, and it's going to be on the upper half of your sky, so it's easy for you to kind of find for those 10-day period. And let's see, and Crux is the constellation that's used actually in the southern hemisphere, but for the people in the northern hemisphere, it is Bootes the Plowman, they call him. And here you see the first 3 of the 7 charts. You see how the numbers of stars increases as the chart numbers get higher, and because you're seeing fainter stars, as I mentioned. And it means that your night sky brightness is decreasing as you go to higher and higher numbers of the charts. You have less and less light pollution. So the chart you choose to match what you see in the night sky is a measure, therefore, of the light pollution level. And again, you're not counting stars, you're just finding the faintest star that you can see in both circumstances. So as mentioned, the different levels of 1 through 7 shown here, well, you'll see the other 4 in just a second, denote different levels of light pollution. So there you go. There's levels, charts 4, 5, 6, and 7. And there you see on the screen Bootes, what the shape of him is like. As you go to higher chart numbers, you see more and more stars. And this next one here is actually the cloud cover. You have one question on what your weather basically is like, and it's the same thing as asking how much cloud cover you have. And the first one will be no cloud cover, obviously, and the last one will be totally socked in, basically. So hopefully it's not that last option where it's totally cloudy, because we actually cannot at this point use that data, unfortunately. So I hope you take your measurements on what is hopefully a pretty clear night. I mean, at least clear towards the constellation that you're looking at. Another thing you can do, but it's optional, you don't have to do this, you don't have to input the data if you do not have this, is use a sky quality meter. And this is cool because it's a device that actually takes a measurement, and it's very objective, basically. It's not subjective, right? It's a battery powered device, and it actually is made by a company called Unihedron. And if you want to buy one of these things, just for if you think you might want to do that, please contact me. We do have a little bit of a discount that might benefit you. So again, it's called a sky quality meter, and you can put that in step number 5, I believe, but you don't need to if you don't have the data. Optional. And then you just hit the submit button. And this is a summary of the 6 steps. When and where you made your observations, steps 1, 2, and 3. And also step 4, you're choosing your chart. And notice here in this particular step 3, I should say, where you're going to choose your chart, you have 7 or 8 different thumbnail images at the very bottom of the screen where my cursor is. And by clicking on them, the one that you choose appears in this bigger part of the bigger picture here on the screen. And where you leave it is your measurement. So just kind of, oops, sorry. I have a trigger happy mouse. I apologize for that. And then where you leave it is what your choice in measurement is. And so let's see. So to note a few things, the web app you're using is actually a web page that can be used on any smart device and by any browser. So there is a big win-win situation there. And you can go into night mode as well, and it'll give you a pinkish screen. It won't be a light source blinding you from seeing the stars where you are. So that's a good thing. And and also remember that the smartphone, you can get your number 1 and number 2 automatically inputted. And step 3, we already went over. Good. Okay, I'm just looking at my checklist here. And when you have matched what you see in the night in the sky with a chart, you leave your choice there. Don't move it, and that'll be your light pollution measurement. Let's see if I can go to the next one. Okay.
And Connie,
so I just thought I'd go.
Have questions from the audience.
Okay, I just want to see, make sure we have the time. Okay, so it's 5:30 now. That's good. So we still have a little time, right? Or maybe not.
We have like a minute left for your presentation.
Okay, I just like to mention that there's a few ways the data can be used. The primary one is monitoring changes over time, because if things get worse, then you have to do something about it. And one thing that a bunch of high schoolers and some amateur astronomers did was take a lot of global night data, make a map, present it to their city council, and get the laws strengthened in their city, which took a couple year period, but they did it and they were very, very successful. Kudos to them. And the bright dots mean bright skies, the dark dots mean dark skies in this image. Another one was with the lesser long-nosed bat, a threatened and endangered species of bat. A study was done where they went from the Saguaro National Park, where they slept, and to where they ate at like 25 kilometers away, and come back every morning. And it was deemed that the corridor that they usually reuse avoided city center and should be more protected. But a study showed that that was not quite the case. It was one of three factors, and they didn't have to strengthen the laws for light pollution. So there's all these different things you can do. And to help out, here are the Globe at Night dates. The next one again is May 2nd through 11th. And we hope you'll join us. And thank you very much. And I'm open for questions.
Thank you, Connie. So one question from Liz Fleming is, does outdoor home LED lighting pollute the sky more or less than traditional lighting?
Well, it does depend on what kind of, how bright they actually are, what they call a color temperature, actually, a kind of light. So if you look on the package, see how many lumens they are. You want to get something that's equivalent to something lower, like 13 watts instead of a 60 watt thing, for instance. I'm just giving examples. So you want to take something that's not as bright, and you can do that. And they do have their pluses. They're energy efficient, and they last longer. So there are some pluses, and you want to take ones that don't have a lot of blue content, that they're a little more yellowish or even borderline reddish. So those are the kinds of things you're looking for.
All right, thank you. Next question is from Shimi. I believe, hopefully that's the correct pronunciation. So Shimi asks, is there any city in the world with regulations about shielding the streetlights or external sources of light? Is there any campaign to create laws to reduce light pollution? And I imagine the organization that you are a part of with Globe at Night and the Dark Sky Association, that's part of your objective, I'd imagine.
Mm-hmm. Yeah, well, two cities that come to mind immediately are Tucson, Arizona, which has very good lighting laws, but still has challenges to overcome. But the one that's called the first dark sky city is actually Flagstaff, Arizona. And they've led the way for a long time, and by implementing really, really responsible lighting. And a lot of them being LEDs, or what they call phosphor, amber colored LED lights. So they're a good example of a city to follow in terms of their lighting ordinances, as is Tucson. And let's see. So there's a program at the International Dark Sky Association for communities and their efforts to do good lighting. And they also have at the International Dark Sky Association model lighting kind of ordinances that you can look up and follow and see and adapt to your needs in your city. And there's a lot of good advice you can get from them as well.
Thank you very much, Connie. That was great. So we're about ready for our third speaker today. Aaron Meisner is an astronomer at NSF's NOIRLab in Tucson, affiliated with Kitt Peak National Observatory. Aaron works on Kitt Peak's Dark Energy Spectroscopic Instrument, or DESI project, a newly installed spectrograph with the Mayall 4-meter telescope. DESI can observe 5,000 stars and galaxies simultaneously and is making the largest ever three-dimensional map of the universe. Aaron specializes in building astronomical maps using large data sets at visible and infrared wavelengths. He uses these maps to search for moving celestial objects like neighbors to the sun and hypothesized planets in the far reaches of our own solar system. To this end, Aaron co-founded the popular Backyard World's Planet 9 citizen science project. Aaron received a bachelor's degree from Stanford University and earned his PhD in physics from Harvard University. Before joining NOIRLab's scientific staff, he was a Hubble Fellow at the National Optical Astronomy Observatory, the predecessor to NOIRLab. So welcome, Aaron. You talked about this last year, but I think you have some new discoveries since then, don't you?
Yeah, great. Thanks a lot for the introduction, Rob.
Take it away.
So today I'll be talking about discovering nearby brown dwarfs with the Backyard Worlds Planet 9 citizen science project that I co-founded. It launched in 2017. And actually what you're seeing here in this animation in the background is a really cool visual of one of the discoveries made recently by one of our project citizen scientists. It's a brown dwarf that's orbiting a white dwarf actually right in front of the Milky Way galactic plane. So all the background stars made it hard to see for many years. And then all of a sudden, a very observant citizen scientist came along and spotted it. So that was a very neat story. Okay, had a little bit of a delay advancing that slide for some reason, but just to give the background and the motivation here as to why we're interested in launching a project like Backyard Worlds and scientifically what's going on. Well, one of the most time-honored quests in all of astronomy going back many hundreds of years is to find the sun's closest neighbors. There's sort of an intrinsic interest, even, you don't have to be a professional astronomer with a PhD to think it's neat to want to know what are the nearest neighbors to the sun and have we actually found them all. For example, could there be a star or a low mass object, what we call a brown dwarf, that's actually nearer than Proxima Centauri, the closest known star to us. And so this diagram here shows the sun at the center, and it shows what are currently known to be the most nearby stars and brown dwarfs. And there are some relatively famous names you may have heard of, like Barnard Star, Alpha Centauri, Proxima Centauri. And what you see in the annotations here is that these were discovered more than 100 years ago now. And the reason they were discovered a long time ago is because they're nearby and they're bright stars. And so you can see them emitting in visible light where historically most of our telescopes have been looking. But what you see if you go slightly further outward is now some of our very closest neighbors are these maroon colored objects. They have telephone number names that start with things like WISE. And I'll get to what WISE is, but it's a new telescope launched about 10 years ago. And it really revolutionized our view of the universe at infrared wavelengths. So these are wavelengths that are like 10 times longer than the peak wavelength at which the sun emits. If you ever see these infrared pictures of like people or something, you see that the human body is kind of glowing predominantly in these wavelengths. So you need sort of your infrared goggles to be able to see these objects. And that's why they were not discovered all the way up until only a few years ago. Right, and so there's this WISE, that's NASA's Wide Field Infrared Survey Explorer. I'll show a little bit more about what WISE is in detail in a few moments. Just to give a little more background about what is a brown dwarf, say, versus a star in terms of why we're looking for them, why they hadn't been found until recently. So the sun is a star with a temperature of several thousand degrees. It's a pretty typical star, but you can go to fainter and colder stars, and the coldest stars are known as red dwarf stars. An example is shown here. But you can go even colder than the coldest known stars, and then you get into a regime that we call brown dwarfs, where these are sort of intermediate between stars and planets. So they're, say, 12 times more massive than Jupiter, up until about 80 Jupiter masses. There's this intermediate range that's referred to as the brown dwarfs, and they're not massive enough to sustain hydrogen fusion in their cores the way that a star like the sun would. And that makes them very intrinsically faint, very cold, and so they predominantly emit at these infrared wavelengths that I was talking about earlier. And so we actually know now that brown dwarfs can go down to temperatures as cold as basically room temperature as we experience it on Earth, or even colder, as cold as the North Pole on Earth. So something like 250 Kelvin. So this is really, on the boundary between what we might call even a planet potentially. And there's a question that still remains open actually as to is it possible to have a Jupiter size and Jupiter temperature brown dwarf that's just sort of floating around in interstellar space with no host star? So as I was alluding to earlier, there's this NASA WISE satellite that's really changed the game in recent years as far as the ability to discover new brown dwarfs very nearby the sun that are super cold and so were overlooked historically. So one thing that's interesting about WISE is that it's a rather small satellite. It's only a 40-centimeter telescope, but nevertheless it's very powerful just because it's looking in this different regime of the infrared relative to what previous telescopes and much bigger telescopes are looking at typically based on Earth's surface, which is visible light. So what you can see here is that WISE is based on a satellite that's orbiting around Earth. And as the Earth orbits around the sun, the satellite sweeps out these big arcs across the sky. And over time, it builds up actually full sky maps covering everything you can possibly see, every direction you can possibly see over time. And by now, it's actually mapped the entire sky more than 15 times, which makes it great for looking for things that vary in brightness, like variable stars, or things that move around like proper motion stars, because you just have all this repeat sky coverage covering many years. So going into a little bit more of the mechanics of how we actually look for nearby stars in data sets like WISE. So the challenge with modern data sets like WISE is just that they're so huge. The raw data set of sky maps is something like 300 terabytes by now. It's many, many tens of trillions of pixels to look at. There's billions of stars and galaxies in there. And most of those stars and galaxies for us are just considered normal background that we don't really care to discover as far as they're the sun's closest neighbors. But one thing that happens is that when you have a nearby star or a nearby brown dwarf is that it will appear to shift in position relative to the much more distant stars and galaxies in the universe. And that's because everything in the universe is really moving relative to us. It's just that when it's nearby to us, it's much easier to perceive. And so this is an example showing Barnard Star, which was shown previously. This is the closest known star to the sun. It's a red dwarf discovered over 100 years ago. And you can see that it's really moving along relative to the background of static stars and galaxies. So this is kind of an old-fashioned technique, but this is exactly how we still do it in backyard worlds. And it's still a kind of a state-of-the-art way of looking for new neighbors to the sun in astronomy. And this is similar to what Knut said, but you might guess that maybe computers and machine learning and whatnot have come in and sort of made the old-fashioned way of just staring at these images totally obsolete nowadays. And somewhat surprisingly, that's actually not the case. It's still best to have human eyes reviewing for true motion versus what we call false positives, which can be any array of issues from detector noise in the data to weird artifacts like diffraction spikes caused by very bright stars. And so it turns out that we still need to look at images like these to just review and make sure that we've gotten the right moving objects and not some junk in the data. So let me show what this looks like now for brown dwarfs in WISE rather than a star in visible light. So what you see here are 8 examples of exactly the type of objects that we're hoping to discover through these extensive visual inspection searches that we do with backyard worlds. In the middle of each of these panels is a very reddish, orangish object you can see that's sort of shifting around in position. And those are the very cold and nearby brown dwarfs that we're hoping to find. But what you can see in each panel is that there's tons and tons of other stuff in the image. I mean, there is some noise, although it's not too bad. But what you see is also that there's some background stars and galaxies that have this more normal blue-white color. And what's going on with that is just that we have billions of those on the entire sky. And so if you were to look at a random patch, you would see lots and lots of these normal colored, sort of whitish, bluish stars and galaxies, and you wouldn't necessarily see one of these orange brown dwarfs flying by across the screen. So the trick is that it takes, typically several hundred random sky patches to look at in order to find one of these examples we see here with the orange moving object. So just some background facts as to where we are with the Backyard Worlds Citizen Science Project as of now. It launched in February of 2017, again, via the same Zooniverse portal, which is really great because many users are already familiar with this. It works great on a smartphone or a computer or any platform. By now, we have more than 7 million user classifications. So a classification is sort of like a unit of effort that can be contributed to the project. In our case, it's like one person staring at one time series image blink of the sky as seen as in WISE. We have over 66,000 registered users. You don't need to register though, so we think that the total number of contributors is closer to 150,000. Similar to Globe at Night, we have quite geographically diverse participation here. We have participations from all 50 United States, plus Puerto Rico and DC, and we have at least 167 countries represented in terms of the people who have partaken in Backyard Worlds, which is really great to see. So now I just wanted to move to highlighting some of our recent fun science results that we've come out of Backyard Worlds. So a few months ago, we announced that our team, including many citizen scientists, has now created the best ever 3D map of brown dwarfs in the sun's cosmic neighborhood. So the neighborhood here is defined to be within about 65 light years of the sun, which is kind of like a gold standard sample that we use. And so each red point in this visual you're seeing is one of the 500 brown dwarfs in that sample. And actually over just the past couple of years alone, we've added about 125 of those newly discovered objects based on our searches in these WISE data sets. So it's really great to think that, over the course of all of astronomy, we had time to find these, but just in the past couple of years now, we've sort of increased the sample by a factor of a fourth, which is quite a lot. So it's cool to also just think about these brown dwarfs in terms of their three-dimensional locations, because what essentially we're doing here is we're mapping out the constellations as you would see them in the infrared with our nearest brown dwarfs, as opposed to how they're traditionally defined with the brightest stars in visible light. Here's another way of visualizing all of our Backyard Worlds brown dwarf discoveries. So within the past 4 to 5 years now, we've discovered more than 3,000 of these brown dwarfs through the Backyard Worlds project, which if you cost it out, it's kind of like 2 per day, which is really neat to think about. What you see here is a visual rendered in 3 dimensions of what these discoveries look like. And so what you're seeing is that each brown dwarf is color coded by its temperature. So redder means colder and whiter means hotter. And so you can see that the colder ones, we can only detect them very nearby because they're just so faint. And then what you see with the motions here is that since we detect them with their motions, we know how they move. And over time, these objects, we can play it forward over millions of years, how they would disperse throughout the Milky Way galaxy. And that's exactly what you're seeing here. So one sort of last note I wanted to highlight is that we take very seriously the idea of trying to find time on the best telescopes on Earth and in space to observe and follow up in more detail the discoveries that are provided to us by our citizen scientists. And we've used many of the best telescopes, including some from NOIRLab, namely the Blanco here in Chile and Gemini in both Chile and Hawaii, as well as Hubble and Spitzer, which are 2 of NASA's great observatories. And so our participants often tell us that one of the best things about the project is knowing that their discoveries were uploaded to something like Hubble or Gemini and sort of told it where to point. Most recently, we actually just a few weeks ago found out we got JWST, James Webb Space Telescope time, to look at a few of the brown dwarfs that I've discovered by our citizen scientists. And so, Hubble, Spitzer, Gemini, that's really cool, but this was kind of a whole nother level of thrilling for the folks who made these discoveries originally. So I just wanted to conclude by essentially saying that we found a lot of brown dwarfs through Backyard Worlds already, but there's still much more infrared sky data left to search. WISE is actually still observing as we speak, day and night. So there's more data always coming in, and please consider joining our search for brown dwarfs. And here's the URL at which you can get started looking at some of this infrared sky data. So I'll end there. Thank you.
Thank you so much, Aaron. Yes, I've dropped that link in the website into the chat, as well as a few of our NOIRLab press releases on what you've all been doing with Backyard Worlds, Planet 9. It really is a fantastic citizen science project, and I do have a link to the Zooniverse in general there and to your project. A few questions, Aaron, before we wrap up here from Our first question is for anyone, but from Liz Fleming, though I think Aaron and Connie, you can both, and Rob, of course, can all answer this. Do the increasing number of satellites and other human-made technological objects in the sky negatively affect our ability to see galaxies or other objects that we may want to see in the night sky?
Connie is the expert on that.
Right?
The short answer is yes. They're getting to be more and more frequent. We now have just a few thousand that are up there orbiting, but the point is, if they're sunlit, and if they're, they affect mostly things like some of the new technology that's going to be coming online in the next couple of years, with wide field telescopes that are imaging, faraway galaxies, and also near Earth asteroid projects, because a lot of these satellites are seen sunlit at twilight and close to the horizon too. That's where the sun is actually, doing the reflecting off of them most. And so, but if they're higher up, they're up there. The satellites are up there all night, seen by different observatories, and so they affect the images. And every few weeks, with one company, I don't want to mention company names, but they're launching every few weeks. So you see a string of pearls, or like a bunch of them bundled together. And it takes them a few weeks to rise to their final location. So you're always going to have that happening. And so there's a few hurdles that we're going through at the moment, trying to talk about mitigation strategies with a couple different companies.
Thank you so much for that, Connie. Yes, you are our expert here on that. Aaron, Rob, anything to add?
No, I mean, it is definitely true that in these large data sets and these rare object searches, one of the types of false positives that you can have, spurious, essentially junk, is satellite streaks going through your image. So that is an effect for sure.
Even just with my astrophotography with the camera and a zoom lens, I get satellites all the time. Not even geosynchronous satellites I can photograph easily with a camera and a zoom lens.
That's really surprising that you could actually see it just if we're doing some regular amateur astronomy and we have some equipment set up, that it could actually affect what we're able to see. I didn't realize that. But it is good to know. All right, and it looks like we had one more comment. Aaron, if you could say more about JWST, which is the James Webb Telescope, Space Telescope. I put a link there, but Aaron, if you could maybe end for us with giving us a highlight about JWST and why it's amazing and important that you all got JWST time.
Right, so JWST, the James Webb Space Telescope, it's kind of like a successor to Hubble Space Telescope you can think about, but in terms of that way. But one thing that's special about it is that it's really optimized to do this infrared wavelength observing in a way that Hubble wasn't. And so it's kind of the perfect instrument to do for looking in detail at these very coldest brown dwarfs, say the room temperature or North Pole temperature brown dwarfs. And so there was a big rush over many years, including backyard worlds, to find the best possible brown dwarfs to observe with James Webb Space Telescope. And so it's really awesome to see that several of the objects discovered by our citizen scientists were viewed so highly by the community that they were chosen among all the possible brown dwarfs to look at with this very, very precious JWST observing time. So that was a really fun highlight for our project.
Thank you so much, Aaron of Backyard Worlds Planet 9. All right, Rob, back over to you.
Okay, I just want to mention Alan Jackson's comment. It's not a question, it's a comment, but he said he'd love to see these visualizations on an Oculus Rift or other 3D VR viewing goggle. And that would be cool. So to have something like that. So,
yeah.
Anyway, thank you very much, Connie. Thank you very much, Aaron. These are great. And of course, thanks to Knut in absentia. And before we go, Jamika, I believe next week is live from NOIRLab at Gemini, correct?
Yes. Next week is live from NOIRLab at Hawaii. We will have as our guest Dr. Jacob Bean talking about the first science results from Rune X, Gemini North's new exoplanet finding instrument. So same channel next week right here, 5 p.m. MST, 2 p.m. HST, to find out more about Maroon X. Thanks for that, Rob.
Yes, and I had the pleasure of interviewing Dr. Bean a couple months ago, and he is a fantastic speaker. So I think that you will enjoy that immensely. So I encourage everyone to tune in for that one. So without any further ado, we're going to be signing off for this week's Live from NOIRLab at Arizona. So bye, everyone, and we'll see you.